So again, this is what I said in the first slide. This surface is not stable. If we expose it to the ambient, we will have an oxide intersection in between the silicon lattices here, and we will have an OH termination being formed. We typically call this a native oxide or a chemical oxide. It's a slow process because you can see here, this is the amount of oxide that is being formed, or the thickness of the oxide in the order of nanometer here, or 1 nanometer here, so sub 1 nanometer here, as a function of time. So it is an unstable surface, but it is a relatively slow process. Why? Among others, because oxidation is determined by the concentration, is determined by the temperature. So at ambient room temperature, with ambient concentrations of oxygen in the air, it is a slow process. But what you need to remember here is that if you would leave a surface exposed, you will have a chemical oxide being formed, or a native oxide being formed on the silicon surface, and the thickness is typically in the order of 1 nanometer, as a rule of thumb type process. Now, in many cases, we need a thicker oxide. We need an oxide in the order of several tens of nanometers formed on the silicon surface. And in those cases, we will use a thermal process, so we'll use high temperature to achieve this oxidation process. Now, we distinguish here between a dry process, which is the silicon exposed to oxygen vapor, or a wet process, the silicon exposed to water vapor. And in both cases, the end product is an SiO2 layer. You've seen this image on the first slide. So this is the crystalline structure of a silicon wafer, on which we start to do an oxidation process. And this, well, shady area here is basically the SiO2 that is formed on the silicon. Now, in order to form the SiO2, we need to consume silicon. And that is what I'm trying to explain here. So this is the bulk material. This is this area here. This grayish area is that area which is intersected by the red line here. And this is the dashed line is representative to the red line here. If we start to do an oxidation process, the oxidizing compound arrives at the surface and will convert the silicon. Now, in order to convert the silicon, it will basically have to diffuse to this oxide layer and undergo a surface reaction here. If it undergoes a surface reaction, silicon plus oxygen, there's a volume expansion. So the material grows above and below the original surface. So with an oxidation process, we basically will have oxidizing species diffusing over the oxide barrier, reacting at an interface that is gradually going deeper and deeper into the substrate, resulting in a layer that is being formed on top. And the conversion rate is typically that you would actually consume about 45% of your silicon substrate to make 100% of an oxide thick layer. So you have an expansion and a diffusion over a process. It's an amorphous layer, so contrary to quartz, which has a crystalline ordering, the silicon dioxide that is achieved by thermal oxidation or by chemical oxidation on the surface will result in a amorphous structure, so there's no long-range order present in that surface. For the experts, you can see this. Here you have the nice crystal lattice, so the silicon atoms align here, and here you have an amorphous or a more random structure. There's a little bit more information here. The density of such an amorphous layer is less than the density of quartz. There's some other properties here, but important to realize is that you will always have within that matrix also those silanol groups, so the hydroxylated groups, not only present at the surface but also in the bulk of the material, depending on the density of the oxide that you form. Now, what I would like to come to is this specific case of oxidation, of thermal oxidation, that is described by Bruce Deal and Andy Grove. Two names that may sound familiar. Yes, these are the two people that were involved in the founding of Intel. But before they became rich with the company, they also worked as scientists, and they developed a model for oxidation. Why was this so important for them? Because the heart of a transistor is basically oxidized silicon dioxide, or at least until a few generations ago it was oxidized silicon. So understanding how the silicon substrate was converted into a high quality silicon oxide was important for them, and that's why they devoted a lot of time and effort on understanding and coming up with a model that describes the thermal oxidation of silicon, at least for thicknesses above 10 nanometers roughly. It is again a process of three terms. You have a conversion or a transport of gaseous oxidizing compounds from the gas to the interface of the oxide that is being grown. Then you have a conversion from gaseous compounds at the interface to dissolved oxidized species in the oxide. You have a diffusion of the oxidizing species over a diffusion layer, and you have a surface reaction here. Very similar to the three steps that we described in the cleaning step. You have a surface reaction, you have a diffusion over a boundary layer, and you have a transport in the bulk, in this case, of the gas. So three compounds, a flux 1 gas species going to the surface, diffusion of the oxidizing species over the growing oxide, and a surface reaction. There's a little bit more explanation here, but the first flux are the oxidizing species from the bulk of the gas phase to the gas oxide interface. That flux can be described as a mass transfer coefficient and the difference in gas phase concentration and surface concentration. For this particular derivation, they do a conversion to make sure that it's expressed in the same units. They use the ideal gas law and Henry's coefficient to convert this from a gas concentration, surface concentration, to again, a bulk concentration and a surface in the oxide that can basically diffuse. There's a little conversion of the mass transfer coefficient, which now goes into a factor H. The conversion is basically described here, but it is nothing more than using the ideal gas law and putting all of the constant terms plus the temperature in the new defined H factor. But for the sake of understanding of the process, there's a first flux that transports the oxidizing species from the gas phase to the interface. There's a second flux, which is described by a diffusion law, the diffusion of the species over the growing oxide. So there's a diffusion constant and a concentration gradient over the growing oxide. That's your second term here. And then the third term is basically a reaction rate determined flux, the speed at which the species react away at the surface, described in a first order chemical equation. Now if you reconvert all of those terms and you assume that under steady state conditions there's a balance between the flux 1, flux 2 and flux 3, then you can basically rework this equation into what is called the Deal growth equation, and it's a quadratic description of how the oxidation process happens. So there's the oxide thickness is the quadratic term, and there's a constant factor A and B that is being described, and then a factor T, the time, because indeed the longer it takes or the more time you have, the higher or the thicker the oxide will grow. And there's a factor tau, which is an offset for the initial oxide that is present. So you may have some oxide present on the surface when you start the process, and that gives the time offset, because it would have taken a certain amount of time to grow that initial oxide. Now, I'm just going to go immediately to this slide. So you have the quadratic equation here, and you have a description for what the A, the B, and the tau term would be. Now, what is important in the oxidation process is to understand that there's high order two limiting situations. You have a long time situation, and you have a very short time situation. If you work at relatively long time, you will have a thick oxide present on the surface, and the time is long compared to the initial offset, and the quadratic term will dominate over the linear term here. So you can basically say that at long time it's a quadratic expression, and you have B or beta or B being defined as the parabolic rate constant. Now if you look at B, it is, besides of the concentration and the unit volume, it is depending on D, the diffusion constant. So at high or long times, the oxidation process becomes diffusion limited. That is, if the oxide is so thick, it takes a long time before the species can basically diffuse through that growing oxide, and whatever species makes it to the interface with the silicon will react away. But it's the diffusion that limits the process, and that's why you have the leveling off, that's why you have the parabolic growth. For very short times, the equation can be written like that, and it's controlled by the B over A factor, which is the linear rate constant. Now if you write B over A, then the diffusion basically disappears from this, and the reaction rate constant, so the speed of reaction at the interface, remains as the determining factor. So at short oxidation times, everything, it's the reaction rate, the speed at which the species can react away, that determines the growth of the oxide. So it's a reaction rate limited, and in the initial phase it is a linear growth, and then it starts leveling off to a parabolic growth. That is what you would see in this graph here. So this is at relatively short time, it's a linear growth, and at longer growth times it converts into a parabolic growth. So two limiting cases, one that is controlled by the reaction rate, that's the second one here, and one that is controlled by the diffusion. So process 2 is in the initial phase, process 1 is at longer times. Now, I'm not going to give you more details on this process, other than two specific examples on where differences in the oxidation process come into play. In this figure here, they have the inverse of temperature, and they have here the parabolic rate constant plotted for two types of oxidation. So what I described as the dry oxidation, and what I described as the wet oxidation. Now, whenever you make a plot of an entity as a function of the inverse of the temperature, the slope is the activation energy. And what we see here is that there's a difference in activation energy for the two types of oxidation processes. And the reason, so a dry oxidation has a higher activation energy for diffusion than the wet oxidation process. And the reason for this is that the water molecule is smaller than the oxygen molecule, so it can diffuse easier through the formed oxide. So the diffusion is easier than the diffusion of water. Therefore, for the parabolic growth part, you have a difference in activation energy. Now, if we look at the linear rate constant, we see that the same. In this case, we have the inverse of the temperature, and now we have the B over A factor plotted here, and we see the same slope for the dry oxidation and the wet oxidation, meaning that there's almost the same activation energy on whether we bring the silicon surface in contact with oxygen or with water at the initial stages of the growth. And why is that? Because it is in this case not the oxidizing compound, but it is the energy required to break the silicon lattice. So we have a silicon-silicon bond, which you have to break to do the initial oxidation. That's the reaction that has to happen. And that does not depend on the species that you use to oxidize, but that depends on the energy needed to break that bond. That is why the activation energy is the same in those cases. Here you see, and that's just for information purposes, but you see the effect for wet oxidation and for dry oxidation, the effect of temperature on the A and B parameters. And one thing here, what you see here is two crystal orientations, so the 100 and the 111 orientation, and you will see that the reaction rate, so this term here, the activation energy, is different for a different crystal orientation. And the reason for that is that in one case you have a higher number of silicon atoms and silicon bonds present than in the other case. So obviously the activation energy depends on the number of bonds that need to be broken, and that is higher for the silicon 111 than for the silicon 100. So that's what you have to remember from the oxidation process, that there's a model describing the oxidation process for thicknesses 10 nanometers and above, which is determined by a linear component in the initial process, and which is controlled by a parabolic component for longer oxidation times. The longer component is because of the diffusion, the linear component is because of the reaction rate at the surface.